3, 2, 1. Okay. Alright, here we go. A final topic here for 317. And a final video before we wrap things up. Alright. Okay, thanks for joining me. And so we're going to wrap up our conversation on orthogonal projections, and that will lead us into least squares, which will be the last topic, as promised, to be covered. Alright, so let's talk. Let's recall what we've gotten up to so far. So, a projection is a linear operator on a vector space, so that applying the mapping twice is the same thing as applying the mapping once. Right, note that if V was a Euclidean space, this is a matrix whose square is itself. Good stuff. Alright, as we noted sort of operationally speaking, right, this says that the mapping basically only acts once, because it will take your element, move it somewhere, and then trying to apply it again won't do anything. So it projects you, it moves you, and then that's it. And as we learned, projections split our vector space into two pieces, and you can go in reverse. If you've got a subspace with an algebraic complement n, then there is a unique projection whose range is m and whose kernel is n. And we kind of noted the similarity of this and the rank nullity theorem. The proofs had very similar ingredients. I wonder if there's something going on there. Alright, now, for a finite dimensional inner product space, we demonstrated that if you have a subspace M, then M perp, its orthogonal complement, is in fact an algebraic complement. And we noted that the proof of that is a finite dimensional only situation. We saw in the proof that you had to basically use the Gram-Schmidt process, which is inherently finite. There is a way to go infinite with it, but it basically doesn't work. And in fact, if you are an infinite dimensional inner product space, M perp does not need to be an algebraic complement, unfortunately. So this is truly, as I mentioned, we try to do things in general. We do primarily care about the finite case, but this time around, this is a purely, this only works in finite dimensions. In the infinite dimensional case, you can skirt around here by requiring the subspace M to be closed, which always happens in the finite case. So, anyway. Alright, so in light of all these facts together, then, since M and M perp will give us a clean split of our vector space, that means we have access to a unique projection whose range is M and whose kernel is M perp. And since M perp is all the things that are perpendicular, and they're going to be the things whose output at P is 0, hey, a lot of stuff that's pretty nice is probably going to happen. Alright, this is called the orthogonal projection onto M, and we'll denote it as proj sub M. And, oh hey, maybe that looks familiar if you've taken Calc 3 before. As we noted when I drew the picture, that's effectively what we're trying to get here. Alright, because the projection we know has certain behaviors, we immediately get the following facts. The output of the projection lives in M, and x minus it has to be an M perp, just the nature of being the range and kernel of a projection. We know that M and M perp form that split of the vector space, and once you've got the element that is in the first part, the other one is just x minus it. And if you're already in the subspace, then applying the projection does nothing. Right? Hence the name of this projection, right? If it shoots us into this subspace, if you're already in there, it shouldn't do anything. And indeed, it doesn't. Alright, and something else that is immediate, and this is just from the proof itself, the projection can be computed if we have an orthonormal basis for our subspace. And indeed, it's this computation that we've seen now multiple times. Okay, and we saw in the proof that, this gives you precisely the element A in M that gives you the unique sum. Okay, so this reveals that, hey, if you want to compute the projection, you just need to get an orthonormal basis. So, hey, we know how to do that with the Gram-Schmidt process. Suppose I add m, which is the span of these two vectors right here. If I wanted to project into this orthogonally, well, I first Gram-Schmidt it, and unfortunately, we now see that things might be a little undesirable, because we need it to be orthonormal to do the actual computation here. And yeah, it gives us some pretty gross looking vectors, u1 and u2. Alright, that being said though, equipped with these, we can get the matrix that would represent this projection. It's a linear mapping, so it has a matrix. And we just need to see what it does to the standard basis elements. And in here, these computations are all going to be pretty easy, because dot producting with the standard basis elements just isolates elements. The components, so it ends up being not too awful of a computation. And here we see that we get pretty reasonable things. Not the greatest numbers, but not the worst. Alright, so there you go. So now we can see how to compute it, but it's not the greatest computation, but it's possible to do. Now, what we want to now demonstrate is that there's a reason we care so much about this, even though we see computationally here it doesn't look beautiful. However, per the picture I drew in class, we're expecting the projection to give us nice right angles, and because of that, we're going to expect that things are going to behave very nicely, and indeed they do. The projection is the closest point in the subspace to x, meaning that x minus the projection minimizes the distance from x to y. So, again, we discussed that norm here gives us a definition of length, and with length you can compute distances by looking at the length of a difference. And again, that's just intuitively how things were working in R2. So, hey, here we see that the projection is the closest thing in the subspace to x. Right, and again, we drew the picture and had the right angle, and we're like, hey, this should give us the closest representative here. But we actually have to prove this. And first note that, obviously, the projection of x is an element of M. So the only thing we need to actually verify, and that's should be projection, not P of x there, is in fact, where is that in the slide? Right, we need to prove that that is actually less than or equal to x minus y for all y out of M. Right, we already know it's in there, so it's one of the values, which need to be the smallest. Hence, it's the minimum. Alright, so take an element y that lives in M. Alright, well then, the projection of x minus y is in M, and since x minus the projection is in M perp, that means these are perpendicular to each other, so by the Pythagorean theorem, we know that this sum of the squares is in fact the sum of the length squared total. And now note here, these middle terms cancel, and freaking equal. What is going on with these notes? Oh my god. Oh my god, it's almost like I haphazardly threw them together in the morning when I realized that I wouldn't be able to get to campus. And, you know, life's good. Alright, anyway, there we go. Alright, sweet. So, here we see that because this is an element of M, because this belongs to M, and so does that, and M is a subspace, so the difference is in there. And, since this is in M perp, as we already noted, that means that they're perpendicular to each other, so the Pythagorean theorem applies, and this will have to equal that. Note that this is always greater than or equal to this quantity, because this right here is non-negative. And then we take the square root of both sides, and we get the inequality that we so desired. So again, very similar, very thematic to other proofs that we've been doing in inner product space, where you look at the norm squared rather than the norm itself. But hey, there we go. The projection gives us the closest point, hence why we want to compute these things, even though we just saw the computation might be a little rough. Right, this gives us valuable information. And in fact, not only is the projection the closest point to x in the subspace, it is the unique point with that property. If there is another point in the subspace so that x minus z minimizes the distance, well, then it has to be the projection. Okay, so this proof's basically going to be the same thing as the previous one. the projection minus z must live in M because those are two elements of the subspace. X minus the projection is an M perp, so we pull the same trick as we did before. Note I'm missing a parentheses there. Not that it super matters, but since I'm already laser eyeing all the mistakes and typos in this, it's good stuff. Okay, Pythagorean theorem applies, and this length squared of the sum splits into the sum of the length squared. Right, but what do we know by hypothesis? We know that this is the minimum of that, but we already know that this minimizes it over here. So this and that would cancel, giving me that this is 0, and if that's 0, then it's got to be that the projection of M is in fact equal to Z. Cool. All right, so we now know that we can always find an element that is as close to our element X in a subspace as possible by the orthogonal projection. So naturally, then, we want to go back to Euclidean space and go, hey, what's a subspace I really wish I was in? Well, a subspace I really wish I was in is the column space. So, given a matrix A and a vector B, we say that V is a least square solution if AV minus B is as small as you can possibly make AX minus B, where X ranges through all the elements in A. Alright. So, note that if you actually do have a solution, it is a least square solution because AV minus B would equal 0, and trivially that would be the minimum. So, hey, talking about a minimum distance. So note the name here, least squares, is from the fact that, well, we have a minimum, and we know that this here is a sum of the square root of a bunch of squares, hence the name. All right, well, as we just discussed, you can always find a element in a subspace that's as close as possible by the orthogonal projection. Now, rather than having proj sub column of A, I'll just let P be the orthogonal projection. This lives in the column space, so there is some V that's equal to it. And note that it's going to have this minimum property, but if we think about what this minimum here is, that would have to be that minimum. Hence, hey, least square solutions always exist because they're just whatever the orthogonal projections line up with. Okay, now note, V here, not necessarily unique, because we know that PB is in the column space, so there is a V that works, but we don't necessarily know that it is the thing that works, hence the A least squares rather than the least squares. We'll see a little bit that these are not unique. Alright, great, so that's what least squares are, and we see that orthogonal projections help us out. Now, we've already seen, though, that computing the orthogonal projection directly is not a great idea. So we want to actually get a better method for computing it, and it's going to rely on the best notational result of all time. The null space of A transpose is, in fact, the orthogonal complement of the column space. So the final 4 of the big 4 fundamental subspaces, we now have another way of looking at it. It's the orthogonal complement of the column space. Cool. We're not going to prove this, but we'll note that this is just immediate from the fact that if you look at the Kth entry of A transpose times X, that is the Kth column of A dot product with X. So if you're in the null space of A transpose, this is 0, which would mean that you're perpendicular to all of the columns. And vice versa, if you're perpendicular to all the columns, then you have to be in the null space of A transpose. Right, so I always thought this was a beautiful notational result because, right, you pull out the transpose and you flip it. And I just think it's cute. Alright. So equipped with this, we can now prove that V is a least squares solution precisely if A transpose AV is in fact equal to A transpose B. So here we see that every matrix has least squares solutions, every matrix equation, and they can be computed by solving this matrix equation instead. So rather than solving AX equals B, you multiply both sides by A transpose and you solve that. Alright, so let's actually prove that that's true. So suppose that V is a least squares solution. All right, let P be the orthogonal projection onto the column space. We know that PB is the unique element with the property that it minimizes this distance, but that minimum is that minimum. So it's got to be that A times V is actually equal to the projection of B, right? It's the unique, PB is the unique element that does that, and since AV is an element that works, AV has to equal PB. All right, well that means AV minus B is PB minus B, which lives in the perpendicular of the column space, as we already proven, right? The element minus its projection is in the orthogonal complement, but that's the null space of A transpose, and hey, there you go, we get our A transpose AV is equal to A transpose B. Hey, so again, remember, least square solution will minimize this quantity, but the orthogonal projection is the unique element that does that minimization, hence why AV has to equal PB. All right, and then that gives us that if you have a least square solution, it has to satisfy this equation right here. These are sometimes called the normal equations. Now, conversely, suppose that we do satisfy that. We want to show that you then minimize. Well, if you satisfy that, then AV minus B is in the null space of A transpose, which means that you're in the orthogonal complement of the column space. So if we take orthogonal projection, then everything just revealed itself. Great. We know that the kernel is the orthogonal projection of the column space. All right, well, if that is in the column space, then we know that P of AV minus B has to equal 0 because it's in the kernel of the transpose, the kernel of the projection. PB here just goes on for the ride. Since AV is in the column space, the projection doesn't do anything to it because, again, it's a projection. And solving this then gives me that AV is PB, but PB has to do that minimization, and thus AV has to be a least squared solution. Beautiful. So there we go. Let's actually finish things off by doing a least squares computation. All right, so suppose I want to solve the following system. We can prove that the vector on the right does not belong to the column space of the matrix on the left. So there's no solution. And as we started the course off, we know that when it comes to solving systems with linear equations, one of three things happens. There is a unique answer, there are infinitely many answers, or there are no answers. But when we did that, we kind of noted that, well, even though there's no answer, maybe there's a good enough answer, and now here we go. We'll finish things off by going that there is a good enough answer, always. There's a least squared solution. So you need to solve A transpose AV is equal to A transpose B. If you do that computation, that means you need to solve this. And solving that, here we go. Spoilers. It's possible that you get the solution, and there is, in fact, no unique answer. And we kind of already saw that baked into the actual, derivation. Right, there's no hope that the projection, which would live in the column space, has a unique representation. Just, you could have a pretty defective matrix that doesn't have a great column space, so... All right, there you go. You can prove, though, that least square solutions are unique precisely if the columns are linearly independent. So that'd be maybe a fun exam problem. Oh boy. All right, and with that, we're done. We did it. We covered everything. Next time we see you, we'll do a review, and then we'll take our final exam. So good stuff. Hope you enjoyed our final video and the course. See you next time.